And now let's discuss buoyancy force. And buoyancy force depends on Archimedes' principle. And this is all about objects in water, submerged objects. And of course, that can be generalized to any fluid, not just water. And buoyancy force is equal to the weight of the volumetrically displaced fluid, says Archimedes. So he was distinguishing between mass and volume, which is super, super important. So mass and volume are very vastly different things. And so please review your notes and get those two things distinctly separated in your mental map. Anyway, so what does that all mean? So what's buoyancy force anyway? Here's a surface of water. Here's an object underwater. That object is going to have some weight, which we are familiar with. So the weight is mass times the acceleration due to gravity. I put a CG there just to center of gravity is what we usually call that point. And we can pretend all the forces are coming from that point. And then there's a buoyancy force. The buoyancy force is going to turn out to be the volume of that object times the density of the water times gravity. And isn't that interesting? We're mixing things. So Archimedes says that the buoyancy force, the amount of force that wants to lift that object, is equal to the weight of the displaced fluid. How much fluid is displaced? Well, that would be the volume times the density, but not the density of the object, the density of the water. So that's a really quite interesting statement there. So that's Archimedes' principle in symbols right there. So that means things. It's relevant to whether you are floating or sinking. So we'll discuss floating and sinking. And let's suppose we had water. So the density of water is roughly 1,000 kilograms per cubic meter. And let's suppose we also had a hunk of steel. So the steel is more like 8,000, we'll call it slightly more precise, 7,800 kilograms per cubic meter. So if you had a cubic meter of steel, it would weigh 7,800 kilograms. That is pretty impressive. Let's take case one. So we take let's suppose we had a solid lump of steel. And it's submerged in water, and we want to know if it's going to sink or float. And this is intuitively pretty obvious. If you drop a piece of steel in water, you can guess what's going to happen. Let's take mass, my usual go-to mass, 1 kilogram. Since mass is via our handy-dandy formula, volume times density, that means that volume is mass over density if we just divide both sides by the density there. And so that would be my 1 kilogram made up number over the density of steel, which is 7,800 kilograms per cubic meter. The kilograms will cancel, leaving us with 1.28 times 10 to the minus 4 cubic meters of volume for this 1 kilogram of steel, which, yeah, that's about right. So we're not doing badly here. I do want to mention that shape. So this shape is not relevant. So we could have a lump of steel in any shape. It can be irregular, it can be perfectly regular, it doesn't matter. Cubic, spherical, whatever. All that matters is the volume it displaces. Now, if you're calculating it, yeah, we want it to be a cube or something easy to calculate, but we don't need to calculate it. So let's just compare the weight with this buoyancy force. And weight is pretty easy. Weight is mass times the acceleration due to gravity. I think we know these quantities. The mass was a kilogram, and g is 9.8 meters per second squared. So the weight is not hard to calculate. That's 9.8 newtons, and it's pointed downward. What about the force of buoyancy? Well, that's going to be the volume displaced times the density of water times the acceleration due to gravity. And we figured that out up here. So the volume is this rather small number, 1.28 times 10 to the minus 4 cubic meters, times the density of water, 1,000 kilograms per cubic meter, and then times the acceleration due to gravity, 9.8 meters per second squared. So we'll end up with a force, because the cubic meters cancel with the cubic meters, and then we've got just a mass times the acceleration, which is Newton's second law, so that's good. And we end up with a number in newtons, 1.26 newtons, and that is directed up. All right, so we have a comparison. We've got a 9.8 down versus a 1.26 up. So clearly this steel will sink. It won't. It's not sinking under full gravity. It's not like free fall through a vacuum where we neglect air resistance. It's going to feel a little less than G as it falls because of the buoyancy force. Let's do a quick other case. And in this case, we're going to take that steel and we're going to take a hammer and we're going to shape that steel. We're going to flatten it out and fold it up, and we're going to shape it into a hollow shape. Let's say shell, just to be a little more precise. Let's make it an enclosed shell with volume of 1/10 of a cubic meter. So let's compare our two things. So again, we compare weight and the buoyancy force. The weight is still mass times g. It's unchanged. And it's equal to 9.8 newtons. And then we calculate our buoyancy force, volume times the density of water times g, and that is given now. So we have 0.1 cubic meters. We have the density of water of 1,000. We have gravity of 9.8, and this is equal to 980 newtons, and that is an upward force. So in this case, if we were able to hollow out the middle, then there's got to be a big buoyancy force up. So if we got our water and we've shaped our steel into a shell or something, that shell has a great big force heading up and just a little tiny weight pointing down. So it's quite possible to make, for example, ocean liners and other ships out of steel and still have them float.